Quasi-static process. In the last class we have explained thermodynamic equilibrium and thermodynamic process. Thermodynamic equilibrium means the state of the thermodynamic system remains stationary. Nothing is happening inside the system, or nothing is happening for the system. Its thermodynamic variables remain unchanged. Thermodynamic process means there is a change of state of the system. There is a change of value of any one of the thermodynamic variables. Quasi-static means semi-static. It is a thermodynamic process, but it appears to be an equilibrium state. There is process happening, there is process taking place inside the system, but we cannot distinguish, we cannot identify the process instantaneously. We cannot identify the instantaneous change because the change is infinitesimally small. Change is very, very small. It is microscopically small. We know that thermodynamic process means a deviation from thermodynamic equilibrium. If there is a deviation from thermodynamic equilibrium, there is a process taking place inside the system. In the case of a quasi-static process, the deviation from thermodynamic equilibrium is infinitesimally small. The change is very, very, very small. The instantaneous change is very small. Therefore, if we measure the system, if we observe the system at different instances, we can see that nothing is happening. We can see that the system is always in equilibrium state. So all the states through which the system passes can be treated as equilibrium states. So thermodynamic process in which the deviation from thermodynamic equilibrium is infinitesimally small and all the states through which the system passes can be treated as equilibrium states. Such a process is known as a quasi-static process. Quasi-static process is an extremely slow process. We have two examples. Consider the plant shown in the figure. There is a plant which is growing at each and every instant. If we measure the length of the plant, the height of the plant at different instances, at each and every minute or at each and every hour, if we measure the height of the plant, we cannot see any change, we cannot see any difference, because the change is infinitesimally small. So all the states through which the plant passes can be treated as equilibrium states, or at every instances we can see that there is no change, there is equilibrium. But actually there is a process, there is a slow, extremely slow process taking place. The plant is growing gradually. At every instant it is growing gradually. If we take a large span of time, for months or so, there will be a substantial growth. There will be a significant change. And that change occurred gradually. It is not an abrupt change. That change occurred gradually. So at each and every instant a process is taking place. The growth is taking place, but we cannot distinguish it because the change, the instantaneous change or change in height or the deviation from thermodynamic equilibrium is infinitesimally small. It is extremely small. The process is extremely slow. So it appears to be static, but it is not static. Therefore the name quasi-static process. If the deviation from thermodynamic equilibrium is infinitesimally small, and all the states through which the system passes can be treated as equilibrium states, then the process is known as quasi-static process. It is an extremely slow process. Look at the second example. We have a gas filled inside a cylinder with a smooth frictionless piston, and sand is taken and it is gently poured onto the piston. It is gently poured successively in small quantities, very small quantities. Sand is gently poured. So the force on the piston is gradually and slowly increasing. Therefore the piston is very slowly compressing the gas. It will be very slowly compressing. If we measure the change in volume, pressure and temperature at different instances, at different minutes, at each and every minute, there will be no change. But if we take the change for a long time, for hours, there will be a substantial change in volume, there will be a substantial change in pressure, there will be a substantial change in temperature. So a process is gradually taking place. The gas is gradually and slowly compressed down. So its temperature may increase, but instantaneously there is no change. The process appears to be static. So the system passes through equilibrium states. Such a thermodynamic process is known as quasi-static process. Now let us consider the different types of thermodynamic process. A thermodynamic process means any one of the thermodynamic variables changes. If pressure only changes, it is a thermodynamic process. If volume changes, thermodynamic processes can be done by keeping any one of the variables constant. We can do the thermodynamic process by keeping temperature constant, or pressure constant, or volume constant. Depending on the parameter whose value remains constant in a thermodynamic process, thermodynamic processes are classified into four: isothermal process, isobaric process, isochoric process, and adiabatic process. Here is an isothermal process. First one is isothermal process. Isothermal process is a thermodynamic process in which temperature of the system remains constant. That is, pressure, volume, entropy, etc. changes at constant temperature. So there will be always a heat transaction between system and surroundings in order to make up the temperature changes. Any temperature change can be rectified by absorbing or liberating heat energy. Therefore, the walls of the container should be perfect heat conductors. Consider this example. We have a gas filled inside a cylinder with perfectly conducting walls. Suppose the gas is compressed very slowly. Look at the second diagram. Suppose the piston is moved down, pressed down very slowly. So as a result of compression, when a gas is compressed, heat will be generated. So heat may be generated and temperature of the gas may increase. But in order to maintain constant temperature, the gas will be readily ejected out through the conducting walls. So that temperature remains constant. So pressure increases, volume decreases, entropy decreases, but temperature remains constant. By liberating energy, heat energy, temperature is maintained constant. Look at the first diagram. The cylinder is heated, so that the temperature of gas may increase, but it will be balanced. That energy will be balanced, it will be utilized for expansion of the gas. Such a type of process in which the temperature remains constant is known as an isothermal process. Isothermal process means a process in which temperature of the gas remains constant. From ideal gas equation, we know that PV equal to nRT. For 1 mole of an ideal gas, PV equal to RT. R is the universal gas constant. For isothermal process, T is a constant. Therefore, we can write this equation as PV equal to a constant. This is the equation for an isothermal process. PV equal to a constant. Suppose the state of the system changes from P1 V1 T to P2 V2 T. That is, the process is taking place at constant temperature. Then P1 V1 equal to P2 V2 because PV equal to a constant. This is the equation for an isothermal process. Next process is isobaric process. It is a thermodynamic process in which pressure of the system remains constant. Pressure of the system remains constant. Again, for 1 mole of an ideal gas, we have PV equal to RT. In the case of isobaric process, pressure remains constant. We can rearrange this equation as V by T equal to R by P. On the right hand side of this equation, R is a constant, P P is a constant for isobaric process. Therefore, we can write V by T equal to a constant. V by T equal to a constant. This is the equation for an isobaric process. If the system changes from P PV1 T1 to P V2 T2, then we can write V1 by T1 equal to V2 by T2. V by T equal to a constant, or V is proportional to T. As temperature increases, volume increases in order to maintain pressure constant. V by T equal to a constant. Look at the example. We have a gas filled inside a cylinder. On the piston, a constant weight is placed so that the pressure on the piston remains constant. Heat is given. In order to maintain the pressure constant, as a result of temperature increase, the pressure may increase, but in order to maintain the constant pressure, the piston is raised and volume is increased, so that pressure remains constant. The next type of process is isochoric process. It is a thermodynamic process in which the volume of the system is kept constant. Therefore, work done during this process is zero. Again, for 1 mole of an ideal gas, we have PV equal to RT. Rearranging this equation, we can write P by T equal to R by V. R is a constant on the right hand side of the equation. R is a universal gas constant. V is also a constant for isochoric process. The process is isochoric. Therefore, volume remains constant. Therefore, the right hand side is a constant. P by T equal to a constant. This is the equation for an isochoric process. P by T equal to a constant, or P is proportional to T. As temperature increases, pressure increases because volume is kept constant. As temperature increases, pressure increases. We can write P1 by T1 equal to P2 by T2. As pressure increases, as temperature increases, pressure also increases. Pressure is proportional to temperature. P is proportional to T. P by T equal to a constant. Look at the example. We have a container, two containers of same volume, or we have a container of constant volume. We have a container of constant volume as the gas is filled inside the container having constant volume, and a meter is connected in order to measure the pressure. A meter is connected. When heat is given, the temperature of gas will increase, but the gas cannot expand because the walls are rigid. The container has a fixed volume. Volume remains constant. It is an isochoric process. Therefore, as a result of the heat and temperature, the pressure will increase. That is indicated in the second part. Finally, the pressure increases to P2. There is an increase increase in pressure is indicated in the meter. So when temperature increases, pressure increases in isochoric process. P by T equal to a constant. Next process is adiabatic process. Adiabatic process is a thermodynamic process in which there is no heat exchange between the system and surroundings. There is no heat exchange. There is no heat exchange between the system and surroundings. Entropy change of a system is defined as entropy change ds equal to heat exchanged divided by absolute temperature. So entropy change is proportional to heat exchanged, amount of heat exchanged between system and surroundings. In adiabatic process there is no heat exchange, therefore there will be no change in entropy of the system. Therefore, adiabatic process is known as isoentropic process, because during adiabatic process entropy of the system remains constant. These are the equations for adiabatic process. Adiabatic process is a process in which there is no heat exchange. PV raised to gamma equal to a constant. TV raised to gamma minus 1 equal to a constant. T raised to gamma, P raised to 1 minus gamma equal to a constant. These are the three equations for adiabatic process. We will derive these equations later. So these are the adiabatic equations of an ideal gas. P V raised to gamma, P into V raised to gamma equal to a constant. T into V raised to gamma minus 1 equal to a constant. T raised to gamma into P raised to 1 minus gamma equal to a constant. But gamma is the ratio of specific heats. It is the ratio of specific heat capacity at constant pressure to the specific heat capacity at constant volume. Gamma equal to Cp by Cv. This is an adiabatic system, a gas filled inside a cylinder whose walls are perfect insulators. Suppose we have a cylinder with a piston, with an airtight piston. Suppose a gas is filled inside a cylinder. It has an initial volume, temperature, pressure, etc. Suppose the gas is compressed. Suppose the gas is compressed, the volume decreases and pressure increases. As a result of compression of the gas, heat will be generated. So temperature may increase. If the walls are perfect conductors, if the walls are perfectly heat conducting, the heat generated will be ejected out. So when the piston is slowly compressed, if the compression is very slow, then the generated heat can escape. The heat will get enough time to escape from the system through the conducting walls. Because the process is very slow, the compression is very slow, then the temperature of the gas becomes constant and the process becomes isothermal. If the process is sudden, the generated heat will not get enough time to escape from the system. So even though the walls are perfectly conducting, the temperature will increase for some time. So the process will not become isothermal if the compression is sudden process. So in order to get an isothermal compression, the process should be extremely slow and the walls of the container should be perfectly conducting. Therefore, isothermal process is a slow process. Isothermal process is a slow process. Suppose if the walls are perfectly non-conducting, but in the universe there are no perfect non-conductors. Therefore, some heat will escape. If the process is sudden, the generated heat will not get enough time to escape from the system, so that there will not be any heat exchange between system and surroundings, because the process is sudden and the walls are perfect, walls are non-conducting. The walls are non-conducting and the process is sudden, the compression is sudden, so that the heat generated inside the system cannot escape, will not get enough time to escape from the system. Therefore, the temperature will increase. But no, there will be no leakage of heat energy. No heat will escape if the process is sudden. No heat will escape from the system. Therefore, the process becomes adiabatic. Process becomes adiabatic. For an adiabatic system, the walls of the container should be perfectly non-conducting. But in universe, there are no perfect non-conductors. Therefore, if the compression is slow process, there is a chance for heat to escape. There is a chance for leakage of heat energy. So in order to avoid the escape of heat energy, the process should be executed suddenly. If the piston is compressed suddenly, then the heat generated inside the system will not get enough time to escape. Therefore, the process becomes adiabatic. Thank you.